Hello everyone, welcome to your partner in education, Agile Rank Mate. Today, in this episode of VITEEE Workshop, we're going to be looking at some sample questions of physics so that you can prepare yourself for the VITEEE exam. So today, let's start off with our first question. In the photoelectric effect, initially, when energy of electrons emitted is E0, the de Broglie wavelength associated with it is lambda naught. Now, if the energy is doubled, then the associated de Broglie wavelength is option A, option B, option C, or option D. So, how do we solve this question? Well, we're dealing with the de Broglie wavelength. So, therefore, it's a good idea to know what the de Broglie wavelength formula is. So in order to calculate the de Broglie wavelength, the lambda value would be equal to h over p, where p is momentum. Now, how do we relate momentum with energy? Momentum energy relation goes like this. Energy is p squared over 2m. This is how momentum and energy are related. So therefore, if you write momentum on the left-hand side, it will be the under root of 2me. So 2me, the whole under root, is the value of momentum with respect to energy. So now that we know the value of momentum, let's put it in the de Broglie wavelength equation. So lambda will now be equal to h over under root of 2me. So this is how the wavelength, the de Broglie wavelength, is related to energy. So from here we can find out the relation that lambda is inversely proportional to the root of energy. Now, using this relation, we're going to find out the de Broglie wavelength associated with energy when it's doubled. So let original energy be E0 and the new energy be E dash, which is equal to 2 times of E0. Now the original wavelength will be lambda naught and the new wavelength is lambda. Now, how do we relate lambda and lambda naught? So when we divide lambda with lambda naught, we can, find out, we use the relation 1 by under root of e on the right-hand side. So for lambda, it'll be 1 by under root of e, and then in the denominator, it'll be 1 by under root of e naught. So what we have is, reciprocal. So what we do is we take 1 by e naught, under root of e naught's reciprocal to the numerator of the first fraction. So what we get is under root of e naught over under root of e dash, which is the same thing as under root of e naught over 2 times of e naught. So the two e naughts in the numerator and the denominator cancel each other out. So what we're getting is lambda dash divided by lambda naught equals 1 over root 2. So therefore, the value of lambda when energy is doubled is lambda naught over root 2. So lambda dash equals lambda naught over root 2. This is the correct relation of the de Broglie wavelength when the energy is doubled. So when energy is doubled, then the associated de Broglie wavelength is option A, lambda naught over root 2. The other options are incorrect because we used first the formula for the de Broglie wavelength and also the relation between momentum and energy in the photoelectric effect. So after having done both of that, we find that option A is the right option. Now let's look at another question. In a Wheatstone Bridge, 4 resistors, P 10 ohms, Q 5 ohms, R 4 ohms, and S 4 ohms, are connected in cyclic order. To ensure no current through the galvanometer, one of these adjustments have to take place. Is it 5 ohm resistor connected in series with Q, 4 ohm resistors connected parallel to S, 10 ohm resistance connected in series with P, or 4 ohm resistance connected in series with R? So let's draw the Wheatstone bridge that the question demands. So 4 resistors are connected in a cyclic order. So what that means is that we have P measuring 10 ohms, followed by Q measuring 5 ohms, and you have R on the right hand side instead of the left because we're going in cyclic order, measuring 4 ohms, and S measuring 4 ohms. Now we need to make sure that no current passes through a galvanometer passing in between. The galvanometer is represented as G. So in order to ensure that no current passes through the galvanometer, we need to make sure that we have a balanced Wheatstone bridge. And for that to happen, we need to make sure that P over Q is equal to S over R. So both of these should have a common ratio. Now, if we look at P over Q in the question, in the current scenario, the value is 10 over 5, which is 2. Consequently, if you look at S over R, it is 4 ohms over 4 ohms, which is equal to 1. So therefore, as you can see, P by Q and S by R are not the same. So how do we make sure that P by Q and S by R are the same? So for that, we need to change the values of either P or Q. So P measures 10 ohms and Q measures 5 ohms. The easiest way is to make Q as 10 ohms. So how do we do that? For that, we need to add 5 ohms to the resistor Q in series. So we will connect a 5 ohm resistor to the resistor Q in series. And that option is available in one of the 4 options that we have. So therefore, this is the correct step. So option A, 5 ohm resistance is connected in series with Q, is the right answer. We need to make sure that P by Q reads 1. So for that, we can make it 10 over 10. For that, we'll add 5 ohms to Q in series. The other options do not work. If we add 4 ohm resistance parallel to S, then it becomes 2 ohms, which will skew the relation. 10 ohm resistors connected in series with P would make the difference even more obvious, 20 over 5. 4 ohm resistance is connected in series with R, that would increase R, which would make it 4 over 8, which would make it 1 over 2 instead of 2. So that's also wrong. So all the other options are incorrect because they skew the order. They do not they do not give the relation that P by Q equals S over R. The only option that does is option A, 5 ohm resistance is connected in series with Q. And we need to make sure that P by Q equals S by R in order to make sure that no current passes through the galvanometer in the Wheatstone bridge. Moving on. In the given circuit, initially C1 equals C2 equals C3, and their equivalent value was measured as C. Now a dielectric slab of dielectric constant K equals 3 over 2 is inserted in C2. We need to find out the new equivalent capacitance. So, how do we solve this question? Well, when a slab is added to a capacitor, the new capacitance would turn out to be K times the old capacitance. So if a capacitor didn't have a slab before and had a capacitance C, and then a dielectric constant K is added to the capacitor, then the new capacitance would be K times the original capacitance. So we use this relation for C2. Now, the dielectric constant of K 3/2 is added to the capacitor C2, so its new value, C2 dash, will be equal to 3/2 times C2, which is equal to 3C/2. So this is the new capacitance of capacitor C2. Now from here, we need to find out the rest of we need to find out the equivalent capacitance across the entire circuit. Now, if you've noticed, both capacitance C2 dash and C3 are connected in parallel. So both of these are connected in parallel. Now, when they're connected in parallel, the equivalent resistance, the equivalent capacitance, which is C2 dash 3, will turn out to be the capacitances of C2 dash added to the capacitance of C3, which in this case is 3C/2 plus C, which is 3C plus 2C/2, which is equal to 5C/2. So 5C/2 is the value of C2 dash 3. Now finally, we have the capacitance C1 connected with the combined capacitance here, that's C2 dash 3, and both of these are connected in series. So therefore, when we acknowledge that, we will find out the equivalent capacitance of the whole circuit, which will be calculated like this. The reciprocal of the equivalent capacitance would be 1 by C1 added to 1 by C2-3, which will now turn out to be 1 by C plus 2 by 5C. Now we'll have to make the denominator same, so we multiply 5 to 1 by C. So what we get is 5 plus 2 over 5C, which is equal to 7 over 5C. This is the value of the reciprocal of the C equivalent. So therefore, when you were to invert the fraction, the value of C equivalent would turn out to be 5C over 7. So this is the value of the new equivalent capacitance when C2 is containing a dielectric slab of constant 3/2. So the new value of the equivalent capacitance is now 5C over 7. So option A again turns out to be the right one. So for all of these questions, we've used the underlying principle behind the question and then solved it like a numerical to get the correct option. Now let's move on to another question. Hologram is based on the phenomenon of diffraction, polarization, interference, total internal reflection. Here we will use elimination. Option D, total internal reflection, is used for optic cables. So option D is incorrect. Option A, diffraction, is associated with the sun's corona. So option A is incorrect. Option B, polarization, which is where light rays are, propagated along the same plane and the light that's not in the same plane is blocked. This is associated with tinted glasses. So usually sunglasses and tinted window glasses and stuff, they have a polarized sticker on top of them, which makes sure that less light enters through the glass. So option B is also incorrect. The right answer is option C, interference. So a hologram is taken using traditional videography, except for interference. So basically what happens is that in a traditional photograph or videograph, the light that enters the camera is straight light, and which is not interfered. However, for a hologram, there is wave interference in the light rays that hit the camera. So therefore option C is the correct option. Now let's look at the final question for the day. In the given circuit, all resistances are of 10 ohms. you need to find the current flowing through the ammeter. So we have the voltage V equals 12 volts. We need to find out what current flowing through the ammeter, and we know that all of these resistances are 10 ohms each. Now, if you look at the particular diagram, from point A to point B, we have 4 parallel resistors. We have the parallel resistors which are vertical, A and B, and then horizontal, which are A and B, and then we have the diagonal resistors, which contain the diagonal lines which contain 2 resistors of 10 ohms each. So if we were to redraw this diagram, it would look something like this. We have the potential difference is 12 volts. We have the ammeter here on the negative side. And if you look at the circuit, this will be 10 ohms. These resistors are 10 ohms each, and finally you have a 4th line which contains a resistor of 10 ohms. So this is how the new circuit would look like. This is how the circuit, when you draw it into simpler terms, would look like. Now, the couplet of resistors on the 2 wires of 10 ohms each, both of these are connected in series. So therefore, the equivalent resistor across each wire would be 10 plus 10, that is 20 ohms. So we can use that in order to simplify our diagram even further. So technically now we have 4 parallel resistors and we have their values as well. The top and the bottom resistors are 10 ohms each, and the ones in the middle are 20 ohms each. So now we have a parallel connection, and we need to find out the total resistance before dividing that by the total voltage, which is 12 volts. Now, in this scenario, the equivalent resistance would be calculated like this. So the inverse, the reciprocal of the equivalent resistance is 1 by 10 plus 1 by 20 plus 1 by 20 plus 1 by 10. Since we have 4 resistors, we have to add their reciprocals together. And the common denominator should be 20, and then we will multiply the 1 by 10s so that they read in terms of 20s. So that will be 2 plus 1 plus 1 plus 2. So it turns out we have 6 over 20, which is basically 3 over 10, as the reciprocal of the equivalent resistance. So therefore, the equivalent resistance will now read 10 over 3 ohms. We need to find out the current passing through the ammeter. That's the total current, so therefore that would be the total voltage over the resistance, the equivalent resistance, so therefore that will be 12 over 10 by 3. Now, 10 by 3 is a fraction, so therefore the denominator of the fraction would move on to the original numerator. So that will be 12 into 3 over 10. So that is 36 over 10. So therefore, the current passing through the ammeter would now read 3.6 amperes. So 3.6 amperes is the correct answer to this question. So since this would now read 3.6 amperes, we can conclude that option A is the right option. The other options would turn out to be incorrect because they're not the values that we get when we use Ohm's law to calculate the current flowing through the ammeter. So therefore, option A, 3.6 amperes, is the right answer. Now that concludes this episode of VITEEE Workshop. We hope you found this episode interesting. For more of our useful and interesting content, don't forget to subscribe to Agile Rank Mate, your partner in education. If you want to get the latest updates about VITEEE Workshop or any of our other playlists, then please don't forget to hit the bell icon present below the video. That will give you the latest information from our channel. So until the next webisode, take care, stay alert, bye-bye for now.